Hello, my name is Ausra, and today I will be presenting a brief introduction to the free space optical communication, mainly the communication systems that use coherent light sources such as lasers to transmit data. And unlike the guided optical communications such as the fiber optics, which uses some medium to reflect and transmit the light, here we are not using any medium, barely the free space, as the name suggests. And this technique is used because it provides many advantages and it has a lot of applications. We will discuss them all in details in the next slides. So before we dive deep into the details, I just want to mention that we have space-to-space communication and we have ground-to-space communication and vice versa. So we know that the electromagnetic waves, whether they are radio waves or they are optical, which includes the infrared, visible, and ultraviolet, they all share three things in common. First, they all travel the speed of light, and they are transverse electromagnetic waves, which means they have an electric field and magnetic field components that are vibrating. And all the electromagnetic waves require no medium. So they can travel in medium, but they can also travel in vacuum. So one of the main advantages of having the optical is shown here from the spectrum, but the previous graph was not showing it very well. But this graph is from NASA. It shows it as a logarithmic scale. So as you can see here, the green one is the whole bandwidth or the whole spectrum for the RF, and the whole thing is just 1 terabyte. Well, I mean 1 terahertz. Sorry, which means all these applications, channels, they have to fit within this range. However, for the optical spectrum, because we have much higher frequencies, as you will expect, we will have much more bandwidth to use and to invest. So from the infrared going all the way to the ultraviolet, we have 100,000 terahertz. This whole bandwidth makes it very useful for more applications. So the first thing to consider is the concept of an antenna and what is equivalent for an antenna in the optical systems. So an antenna is nothing but a device that can focus the received beam, such as this one in blue. So we have a received beam and it can focus it on a point. We call it feed horn, or we call it focal or focus point. So that's the purpose of having this curvature. Same thing goes for sending or transmitting. So you will have here the source of the data, and it will send it to the curvature such that we will have a parallel beam of rays. The same thing can be achieved with the optical, since we have lenses. For example, here we have this lens. It's receiving light beam, and it can focus it on one focal on a focus that is one focal length away from the lens. So the real fun starts with this slide. And before diving deep into the details, let's testify the relationship between the wavelength and the physical size of the antenna. The relationship is as follows. The physical size of an antenna is directly proportional to the wavelength, which means higher wavelength needs higher physical size for the antenna. And actually, this is the very reason why modulation was invented as a technique, because say, for example, we want to send a speech signal, and speech is roughly from 20 to 20,000 hertz. So let's say the signal is in 1,000 hertz. This will require a very large antenna, maybe in kilometers long. So it's not really practical. And that's why we modulate it using a carrier signal that has higher frequency. And for the same reason, you can see here that if we want to send like signals from a distance, we will need a larger and larger aperture, which means larger antenna. And that's why it becomes impractical if you want to transmit data from a very large distance. On the other hand, here for the light sources, we know that light, the wavelength of light is very small. It's in nanometers. And that includes actually also the ultraviolet and the infrared. They are close to this range. So this is the first advantage why we want to go to the optical. The second thing is the gain. So let's define what's the gain of an antenna. If you look here for the green for the blue circle, this represents an isotropic antenna, which means a dot source that propagates a ray or a radiation in all directions with equal amplitude. So if the wave is propagating in all directions with the same magnitude, we define its gain to be 0 decibels, which means there is no preferred direction. And on the other hand, if you look on the green one, you see that there is a higher gain. And the reason is because there is some directivity, and we will define directivity in a moment. So if you have an antenna that's, let's say, directing most of the wave in one direction, that means you have higher gain on this direction. And that's why the direction should be always mentioned when talking about the gain of an antenna. So the directivity is an important concept, which is defined as the ratio between the maximum gain in one direction relative to the average of the average radiations caused by the antenna. And one more thing to define here is the main loop and the side loops. So the practical antennas and the real antennas look like this. This is the radiation pattern. It consists of the main loop, which is the loop that we are interested in investing. This is the loop that will transmit the data to be received from another antenna. And we have here side loops, which are the undesired loops. And that's why we need to minimize the magnitude of the side loops, because these loops are just a waste of the power. So as you can see here, for this example, we have negative 20 decibels for the side loops, and we have 0 decibel for the main loop. And that should be always the case, that the main loop is has higher power. So the takeaway here is that the higher the directivity in one direction gives us higher antenna gain. So what is this in terms of the optical? In the optical, we have a much higher benefit because we have no side loops to begin with, which means we have maximum gain. And the reason is because the optical communications use mainly laser beams, and laser beams have coherent light source. And if you look here, this is the procedure that we use. We have first like more than one wavelength and in more than one phase. So then we put them in the pinhole aperture, and we here have especially coherent light, but it has multiple wavelengths. And if we let that pass through the wavelength filter, we will produce a wavelength coherent light, which means a light of one wavelength and is in phase. So all the signals here are in phase, so we don't have any destructive interference. And this source is not propagating in many directions. It's ideally in one direction. But of course, in practice, it will diverge somehow with the distance. This graph here shows how, in principle, the optical antenna works. So for example, here we have the data source. It's being processed if we use it as a transmitter. And then it goes, it's propagated by a laser transmitter. So this laser beam will send the rays. And this is the direction that we are preferring the ray to go. And same, it will work the same, but the opposite direction if we have, if we need to make it work as a receiver antenna. So we will receive the beam, and then we will put it in a photo detector, and then it will go to the data processing. Is the power received or received power for an antenna? This equation works both for the RF and the optical, and it says that the received power is given by the gain of the transmitted and the receiving antennas. And as we just said, the optical will provide much higher gain because there are no side loops. So here I will admit I stole this graph from SlideShare, which is a very useful tool if you want to further make a further study on this topic. So the article name is Free Space Optics. It's on slide 5. So if we use an RF link, the one that's to the right, if we use the RF link, we will expect that the wave we are propagating will go to a much higher distance than the Earth diameter, roughly 100 times the diameter of Earth if we are sending the wave from the planet Mars. On the other hand, if we use the optical antenna here, optical transmitting antenna, it's really very focused. So even though it will go through all this large distance, it will be focused on this area only. So what does that mean? If you look here to the right, this means it will offer us a much higher power efficiency, because if you look for these, this is the area R, and this is here. Sorry, this one here, the one that says A, is the power that we have, because the power here, let's define it as the number of rays that we have on the square area, and the area squared, which is A here. So on the first one, we had 9, and here we have 3, and we have A. So you can clearly see how the rays are attenuated. So if you use this one for the RF link, you will send much more, you will invest much more power, and you will receive very little. And the power is not the main concern here. The main concern is actually the signal to noise ratio. So what does that mean? Signal to rays ratio is the, signal to noise ratio is the how much we have signal in the actual signal in what we are transmitting relative to the noise that we have. So what will happen is that if you send it from Mars using this one, we just said that it will keep attenuating. It will reach here to a level that the noise will be very high relative to the actual signal, which will be hard to detach at the end. So even if you have like an amplifier that's here on the Earth station, the amplifier will amplify both the signal and the noise. So much data will be actually lost. On the other side here, because we said it will have much higher power efficiency, you will have the signal much higher than the level of the noise. So it can easily be detected and separated from the noise. So these two are the crucial factors to have a higher power efficiency and to have higher signal to noise ratio. And this is why the optical is the most favorite way to transmit data for very large disadvantages. So the first, and I think it's predicted, one, it's that it's costly. It's costly because of many reasons. First is because of the photo mixers used there. So what's the mixer? Mixer is a device that is used for modulation. So let's, like here, let's say this is a mixer, and here we have the oscillator. So VCO, voltage controlled oscillator, and here we have the input. Let's call this MT. So we have here the signal that we want to transmit, and it will interact with the VCO, and here we will have a modulated signal. And for RF, the mixers are relatively cheap. You can buy them and use them in your home, or you go to the WAMI lab at USF and use one. But for the optical mixers, they are really very expensive and cannot be easily made. Because the main reason is because the frequency of the light signals is actually very, very high. So it's in terahertz. So you can imagine if you want to modulate, if you want to use it as a carrier and modulate some signal on it, you can just imagine how hard this is. The second disadvantage is that the light signal is actually sensitive to weather conditions and most commonly clouds. And the reason why this is not the case with the RF is because RF wavelength is high enough that it can pass through the clouds, but the wavelength of the optical is very short, so that it gets dispersed when it goes through these obstacles, and it cannot continue. So the signal will be lost with any bad weather conditions. The other disadvantage is the sun. So sun, because it's a high optical source, or an optical source for high, let's say high amplitude, it's interfering usually with the detectors. The last disadvantage is limited point, multi-point accessibility, and we already talked about that, because the array is focused on one particular area. The other ground stations will not get any signal from the space. So here we will discuss the main applications for the free space optical systems. So here we will discuss the process of transmitting data signal MT through an optical channel, an optical system, starting from the first step and until we got to the recovered signal. So first we will send the signal, and then it will go through the optical modulator, which again, it's similar to the mixer, but it's a very complicated mixer in design, which will make the light to be the carrier. So the carrier is here, the light wave, the light signal or light wave. And the data signal could be digital or analog. Then it goes through the driver, which will process this modulated signal such that it's ready to be focused and sent through a laser, by a laser through the free space channel, which is basically the space. And if we are lucky enough that there are no obstacles such as clouds, it will reach to the receiver, and let's call it receiver optical antenna, which is basically like a telescope that will receive this signal, which uses the lens to focus the beam. And this detector, after it receives it, it goes to the optical amplifier. Before it's demodulated, we need this step because although we said that the signal is still way higher than the noise, but because it traveled maybe a million kilometers, something like that, so it really needs to get amplified a bit before demodulating it. And the demodulator is very similar to the modulator, but it works the other way around. So with that, we got to the end of the presentation.